Hello everyone, my name is Filip Marić and I'm a PhD student at the Space and Terrestrial Autonomous Robotic Systems Lab at the University of Toronto in Canada and the Laboratory for Autonomous Systems and Mobile Robotics at the University of Zagreb in Croatia. Today I will be talking about my work in optimizing continuous time joint trajectory representations for locally maximum manipulability in motion planning scenarios. This work was presented at the 2019 International Conference on Intelligent Robots and Systems in Macau, China. During autonomous task execution, actions may often need to be replanned or changed unexpectedly due to external factors. This can be due to changes in constraints, such as changes in obstacle location, workspace geometry, or goal pose, or due to other actions taking priority over the current action, such as the robot engaging in recovery behavior, the user directly teleoperating the robot, or there being a change in control policy. In such cases, it's important to note that the trajectory planned for the current action may affect the success of performing or planning subsequent actions. This is due to planning constraints, which can induce configurations with suboptimal joint space to task space motion mappings in the planned trajectory. A particularly unfavorable case occurs in the presence of singularities, configurations in which the manipulator completely loses a degree of freedom, as can be seen in the two videos below. There, a manipulator follows a Cartesian space path while passing through singular configurations. It can be seen that, while passing through these configurations, the manipulator makes very large and undesirable joint movements. Our goal is to generate an action trajectory such that, in the face of unexpected changes, the robot is able to adapt its motion with minimal joint position changes. Here, two questions come up. The first question is, how do we infer the capacity of a configuration to adapt to action changes? The second question is, how do we efficiently generate a trajectory maximizing this property? To answer the first question, we can consider the unit sphere in the space of joint velocities and how it maps into the task space. We can map the sphere into the task space using the local kinematic mapping, which is a function of the manipulator Jacobian at a given configuration. Using this mapping, we can see that a unit sphere is transformed into an ellipsoid. This is the manipulability ellipsoid, and it describes the manipulator's mobility in the task space directions corresponding to its axes. The capacity of joint movements to produce movement in a task space direction is proportional to the length of the relevant axis. To obtain a more computationally tractable measure of manipulator mobility, we can consider the volume of this ellipsoid. We know that a zero-volume ellipsoid corresponds to one or more zero-length axes. Therefore, we can use the manipulability index, which is proportional to the volume of the manipulability ellipsoid, to indicate whether a given configuration has a singular joint space to task space mapping. We can also use this value to infer whether a given configuration is relatively near a singularity. The manipulability index has previously been used for singularity avoidance in kinematic control schemes for redundant manipulators, which allow for following a Cartesian path with the end effector while maximizing local manipulability. In order to generate smooth trajectories, these methods require small time steps and additional interpolation to maintain smoothness. More importantly, defining Cartesian paths is often not straightforward, and many tasks aren't efficiently described in this manner. Unlike previous methods, we use trajectory optimization to provide an alternative joint space approach. Trajectory optimization methods will modify an initial joint trajectory according to some optimality criterion, while satisfying task-specified constraints. This allows us to generate smooth trajectories from a discrete set of states provided by an external source such as a motion planner. It follows that these methods can also be used to find maximum manipulability variance of the initial trajectory. Optimizing a joint trajectory can also be viewed as performing probabilistic inference, with manipulability maximization corresponding to maximizing the likelihood of singularity avoidance for a given joint space trajectory. This allows us to use a maximum a posteriori estimator to find a trajectory with locally maximum overall manipulability. This approach corresponds to the Gaussian process motion planning paradigm, where the initial trajectory is modeled as a Gaussian distribution generated by a linear time variance stochastic differential equation, represented by a sparse set of support states. In this case, the likelihood of singularity avoidance becomes an exponential likelihood, which depends on the manipulability value in a given configuration. Other constraints, such as collision avoidance, can also be encoded in a similar manner. The trajectory optimization procedure will then correspond to a maximum a posteriori estimator, which maximizes the defined likelihoods in support states. The continuous and sparse trajectory representation also allows us to maximize the likelihood in interpolated states, further improving results. The likelihood of singularity avoidance is defined using a logarithmic function, due to the manipulability value varying by several orders of magnitude depending on the current configuration. The hyperparameters C and M max serve to improve the numerical properties of this likelihood in local optimization scenarios. In this example, we evaluate the performance of our approach on a simple reaching task. We can see that the initial trajectory, shown in blue, starts at a singular configuration and maintains low manipulability throughout its motion. The trajectory optimized for locally maximum manipulability, shown in red, successfully escapes the low manipulability initialization and completes the motion smoothly. A more interesting scenario occurs when we introduce obstacles in the workspace. We can see that the trajectory in blue, generated by a motion planner considering only collision avoidance, passes through near singular configurations while avoiding collision with the table-shaped obstacle. If execution was stopped in these states in favor of a task space control policy, violent joint movements would be generated by moving the end effector. On the other hand, the trajectory optimized for maximum manipulability using the method presented in this paper, shown in red, avoids these configurations while also avoiding collision. We have compared the trajectories generated by our method to those generated by two singularity-robust task space control policies over 50 tasks where the goal is for the end effector to reach a position in the workspace. A trivial initial trajectory is defined for all methods, with the control methods following a straight line in the task space to the goal point, and our method following a linear interpolated trajectory to a goal configuration provided by an inverse kinematics solver. We can see that all methods result in smooth joint motions, with our method always resulting in a fixed execution time of 10 seconds due to the time parametrization of the trajectory. When we consider the average manipulability over 50 such tasks, we can see that our method provides similar results to the better performing control formulation. The same result can be seen when observing the average minimum recorded manipulabilities. However, our method achieves this result in computation times which are almost an order of magnitude lower. Unlike our method, which only requires a sparse set of states, the control methods require dense discretization in order to produce smooth trajectories, which incurs a high computational cost. We also observed that our method generates larger joint velocities resulting from the fixed execution time. There are several limitations to this approach. Firstly, since we are using a local optimization, there is no guarantee that constraints will be satisfied in the solution trajectory, which requires rerunning the optimization. Also, our chosen trajectory representation is time parametrized, which requires us to have some idea of the expected duration of the task, as it heavily impacts the resulting trajectory. Finally, there are cases where the manipulability index can provide false positives, as the manipulability ellipsoid can have a high volume even when some axes are of near zero length. However, we have not observed this in practice. To summarize, as an alternative to avoiding singularities as part of a control policy, our method maximizes manipulability in the space of joint trajectories. Experiments have shown that we can increase overall manipulability in constrained scenarios while maintaining smoothness and low computation times. This allows for our method to be used as a post-processing step for pre-computed motion plans or a standalone motion planner. Thank you for watching, and feel free to post your questions in the comments.